Hello class, welcome back to our 4 intensive multivariable course. In this class, we are going to treat equations of planes and equations of lines in the 3D plane. If this is your first time visiting my channel, kindly press the subscribe button and turn on the notification button so that you get alerts for every class I post. Please watch this video to the end so that you understand every part of it. Don't forget to like and share. So in this course, we begin it with equations of lines and equations of planes in the 3-dimensional plane. In high school, we did equations of lines and planes in the 2-dimensional plane, but in this course, we're going to tackle the R3, that is the 3-dimensional plane, where we have x coordinates, y coordinates, and z coordinates. Representing the plane, you have the z coordinate always pointing up, our x and our y this way. So this is a 3D model. Let's move straight to finding the equations of lines and equations of planes. So let's take the equations of lines. I'm going to draw a plane here. Now, to find the equation of a line, basically you need a point on that line as well as the direction of that particular line. We can easily get the point on the line, but to find the direction in the 3D, gradient of the line wouldn't be the main factor to determine the direction of a line. So in 3D, we employ the use of vectors with known directions. So let's see how we can derive the equation of a line. I have a line in the 3D moving in this direction. On the line, I have 2 points. Say P, naught, and P. So P naught here is a point. This P is also another point on the line. In the plane, I have a particular vector somewhere which has the same direction with my line, and that will give the full definition of this specific line. So that will be here, which is a vector V. So once we have a vector V down here, then I'm going to have this as my origin as usual. From the origin to this point forms a vector, and to this point forms another vector. So this vector will be R naught, this vector will be RT. Once I have this, then here is going to be the vector P naught P, which I represent with a letter A. That is a vector A. So from here, basically, we know that from vectors, if I want to find the vector P naught P, it's simply going to be vector OP minus vector OP naught, where my OP is simply my R, as I have here, RT. Then minus my OP naught, which is R naught, and this is A, vector A. So if I want to find OP, that is my RT, will be simply equal to A vector plus R naught. So this P will be any arbitrary point on the line, where this P naught or the R naught here will be a known point on our line. But this A, which happens to be the direction of our vector, can be gotten from this vector here. We know that this and this are parallel, and for two vectors to be parallel, one will be the scalar multiple of the other. Hence, A here is simply equal to a certain scalar t multiplied by the v vector here. Therefore, my vector equation of the line is going to be RT is equal to my R0 plus TV, that is the vector. This is basically the vector equation of the line. Once we get this, we can get the parametric equations as well as the symmetric equations of the line. Let's see for the parametric. Now this RT, as I said, is any arbitrary point which we don't know the value. So we assume it to be, there is angle. This angle is used to represent vectors. X, Y, Z is equal to the R naught is going to be a known point, X naught, then comma Y naught, comma Z naught, plus T open brackets, our vector, which represented with A, B, and C, known as the directional vectors. And the numbers are directional numbers. So they show the direction of the line. Once I have this, by equality of vectors, x is simply equal to x naught plus at. And y is simply equal to y naught plus bt. Then my z is simply equal to z naught plus ct. And this is what we call the parametric equations of the line. Then I go to the symmetric. Now, the symmetric is saying that there are cases where the direction of the line will exactly fall. They will give you 2 points on the line which you can find the vector. Hence, t wouldn't be needed. So we can make t the subject from each. So x minus x naught over a will be equal to t here. Y minus y naught over b will also be equal to t here. Then z minus z naught over c will also be equal to t here. Once you have this, you equate your t's and you are going to get x minus x naught over a is equal to y minus y naught over b is equal to z minus z naught over c. This is what we call the symmetric equation of a line in the 3D plane. Once I have this, I move on to finding the equation of a plane. So for a plane, I'm going to draw another 3D plane for consideration. I said always the upward is your your z plane. So I'm going to draw this here. If I have a plane looks this way, it's a 2D. If I have a plane in this 3D, then a plane is defined by what we call the normal vector. So we have a particular vector which is perpendicular to every point in the plane called the normal vector n. This vector, I said, is perpendicular to any point in this plane and is used for defining the direction of the plane. So let's see how to get the equation of a plane. Now, you have 2 points in the plane, and these points will be such that you have P and P naught. So P and let's say P naught. So this P will simply be a vector from the origin as this, then this P naught from the origin, then this P from the origin. So once I get this, I can join P and P naught to form another vector. Hence, here will be a vector R and here will be a vector R naught. Then I'll get my vector P naught P. So to find vector P naught P as we did in the previous part, you're going to get OP minus OP naught, which is equal to RT minus R naught. So this is the vector representation of P naught P, the vector P naught P. And now this vector P naught P happens to be in the plane. Therefore, as the statement goes, any vector in the plane is perpendicular to the normal vector. Therefore, applying dot products, the normal vector dots R minus R naught should give us 0 because they are perpendicular. You know that if the angle between two vectors is 90 degrees, their dot product is 0. So that is how we got this. So our normal vector, as I said, is A, B, and C. So this is the vector equation of a plane. Let's go to the algebraic equation or the linear equation. So ABC dots, my R is x, y, z, minus my R naught, which is x naught, y naught, z naught, then should be equal to 0. Should be equal to 0. So at this point, I'm going to get A open bracket x minus x naught plus B open bracket y minus y naught plus C open bracket z minus z naught is equal to 0. And this is how we get the equation of a plane. Let's solve some few questions I have here so that you understand how to apply this. The first problem is determine the equation of the plane of the line that passes through the points 0, negative 3, 8 and is parallel to the line given by s is equal to 10 plus 3t, y is equal to 12t, then z equals negative 3 minus t. So from this we can say that we have two lines into consideration. They are parallel. Once they are parallel, they will have the same direction. Therefore, the directional vector of this line becomes equal to the directional vector of the line you want to find. Therefore, the directional vector here is simply the coefficient of the t's. So here will be what? 3, here will be what? 12, and here will be what? Negative 1. So let's see. Our vector is simply equal to, our v is equal to the 3, 12, the negative 1. Then they give us a point 0, negative 3, 8. 0, negative 3, 8. So when you have this, we can write a simple equation so that we have R is equal to R naught plus Vt from the equation. Therefore, you will simply have our R to be equal to, so I'm going to have x, y, z, which is any arbitrary point, should be equal to my R naught, which is 0, negative 3, 8, which is in the vector form, plus t open bracket 3, 12, negative 1. Therefore, since the question gave its equation in the parametric, we leave it in the parametric. So we get x to be equal to 0 plus 3t, that will give us 3t. Then also our y will be equal to negative 3 plus 12t. Then finally our z will be equal to this one, 8 minus t. And that gives us the equation which is parallel to that line. Now let's see, you solve this equation or this question you have here in our next class. Don't forget to join that class. Thanks for joining this class, and make sure you share, like, and also subscribe.